I want to talk about how we pick the correct hypothesis test to use on the AP exam. And in this video, I'm going to talk about not only how we decide which test to use, but also what the null hypothesis would look like, and what the conditions would look like, and what that test statistic would look like at the end. If you want more details about the actual hypothesis test and to see fully worked examples, please look at my other videos on the individual tests and topics. To begin with, the first thing I would look at is my information being presented dealing with sample means. Okay, so averages. And a nice, besides context clue where it'll talk about, an average or something, a nice secondary thing to look like was a deviation provided to you, a sample deviation. So if they said something like, we took a sample and it had an average of 13.2 with a sample deviation of 2.1, seeing that deviation should right away tell you, okay, so I had an average and I had a deviation. Proportion problems, count problems like chi-square tests, things like that, those will not have a deviation, but means will. So that's the first thing you do is you just say, okay, is it a mean? Does it have a deviation? The next thing, if it is a mean, if the answer's, yes, the next thing I would do is count the samples. So you either have one sample with just like one piece of information, or you might have one sample with two pieces of info. I'll come back to that in a second. Or you might have two completely different samples. Now, if you have one sample, so you say, well, I took a sample of 40 and it had a mean of 13 and a deviation of 2 or whatever, you have one specific sample, that leads you to a t-test. And a t-test has a null hypothesis that is always mu is equal to whatever number was given to you. So, if they say, well, the mean used to be 12, but we have the sample of 13, you'd say, okay, so the null is that mu was 12. The alternative might be, greater than or not equal to, whatever. You would have to come up using context of the problem for what the alternative would be. Now, the conditions for a t-test are, first of all, is the sample size less than or equal to 1/10 the population size. I'm going to use through this video, just for the sake of space, this is my sample size, this is the population size. And this is our first condition that is there to ensure that we do have variability. My next condition has to do with central limit theorem, and that is that I'm looking for samples larger than 30. Now, if we don't have a sample larger than 30, we do have an out for this. We could be given information about the sample that would allow us to maybe make a box plot or something to make sure there's no skew or no outliers. Or we could be told that, hey, the original population was normal and we took a sample of 15. If the original population is normal, we can get away with a smaller sample size. So if the sample size does not achieve this, reread the question to see if we were given some information about the original population, or maybe we've even given enough information about the the sample to know that there was no skew or outliers in our sample. All right, if we have a sample but we have two pieces of information, for example, we took a group of people and we took their blood pressure and then we had them take some blood pressure medication and took their blood pressure again. We had one sample, but we collected two pieces of information from each person in our experiment, a before and an after. Or maybe you have a sample of 20 cars and you check brake pads on each car and then you put in brand new brake pads and check those brake pads. Well, again, you had a sample of 20 cars, but you took two pieces of information. This is what's called a matched pair t-test, and this is always a little tricky because there is no special thing on our menu of tests on our calculator for this one, but it is a matched pair t-test. And essentially we run it as a t-test where our null is always that mu is equal to 0. We don't even have a number to fill in because we're boiling everything down to kind of one set of information. And that's the difference. U is the difference. I'm going to make a note here. U is the difference. Okay, now in terms of the conditions, it is the same two. I'm just going to draw arrows here. Same two conditions for this. Okay, so we're still checking that our population is, my sample's 1/10 the population. And again, I should be looking for 30 or more information. Now, if instead I had two separate samples, like two samples with sample sizes, that's often the way to kind of count sample sizes. Then we're doing a two-sample t-test. And the null is that the two means are equal. The alternative could be that they're not equal, one's less than the other, whatever. Now, in terms of the conditions, I'm going to take this, draw down here, this one, draw down here. The only difference is we have to do them twice, once for each sample. We didn't have to do that here because we only had one sample with two pieces of information, but here we had two separate samples. So we would check each sample in this way. Now, the test statistic for all of these things is a t-statistic. So it would end by us saying, okay, t is equal to blank, and of course we'd report a p-value for all of them. Just remember, I'm going to put a little circle here, we need to include a degree of freedom. And I'll just make a note, it is always the sample size minus 1 degrees of freedom. And for the case of the two sample, we use the smaller. We're only as accurate as our smallest sample size. Okay. Now, the other thing in here is, if you're writing this on the AP exam, you should define your parameter. You should write, well, the null is 12 and mu is the average, amount of air in the tire, something like that. Match pair, mu is 0, mu is the difference between before and after. In two samples, you should write a subscript that will explain, mu of the under 30s is equal to the mu of the over 30s or something like that. And obviously, your test statistic is a t, but you'll also then report a p-value, and then you'll make a conclusion. Again, if you want more examples of that, be sure to look on my other videos. Okay, let's say it wasn't a sample mean problem. Let's say instead it was a proportion problem. So we'll put a no, it wasn't. Now, we go to proportions. And proportions, first thing is there is no deviation given. So that's your big clue here. But also things will be given to you as like 15 out of 25, or you'll be given an actual proportion or something like that. But you're looking for like sample sizes and amounts out of that sample size, like a count or something like that. Now, once you've determined, and I always look at means first, once you've determined that it is a proportion problem, then you count samples. So if it's one sample, you're doing a one proportion z-test. If there are two samples, you're doing a two proportion z-test. So the number in front, this right here, simply on your calculator refers to how many samples there are. And the z is, we're going to use the z-statistic. That's going to be our test statistic for this. There is no t-test for proportions, and I'll explain when we get to the conditions. Okay, so our null for this will be that p is equal to some number. Of course, our alternative will be that it's not, greater than, less than, not equal to, whatever the context says. For a two proportion, it will be that the first proportion is equal to the second proportion. And as with means, in a situation like this where you only have the one sample, you should explain, P is the proportion of people that whatever the context is. Here, you're allowed to use just subscripts, but give your person, your grader, some clue. Proportion of men is equal to the proportion of women. Use some kind of subscript to tell them. Okay, now the conditions, first off, we have this one again. Sample size has to be less than or equal to 1/10 the population size. Condition 2 is that our sample size times our proportion has to equal a number that's greater than or equal to 10, and n times the complement of that proportion. Now, I'm putting these little blanks here because you do need to include the number. You can't just write n times p is greater than or equal to 10. You have to say your actual calculation. Show the greater that you did actually calculate it. If you're doing a one proportion z-test, of course, these are your conditions. And I'll just draw an arrow quick. These are it. But if you're doing a two proportion test, of course, you have to do it twice. Once for each of your samples. Now, our test statistic for this is the z-statistic. In both cases, we'll report a z. And because of that, there is no degree of freedom. One other condition I just wanted to highlight that you should be putting, and I wanted to wait until I had both of these kind of put up. If you have two samples, the one condition that you should add in is that they are independent samples. Okay? So not only should you mention the, n is less than or equal to 1/10, n is greater than or equal to 30, or down here, the independent samples, that, these conditions, you should include that they were independent samples. They didn't have anything to do with one another. Okay? These are kind of the first big ones. Okay? So now, if you are at the point where neither of these have been met, then I start looking first off for regression. Okay? So a regression equation, this is doing a test for the slope. This will be fairly clear from the context. They're going to want you to test the slope. And they're going to say something like, do we have evidence of a positive linear relationship or something like that? So read carefully, but I think this one's going to be very clear that it was not a mean or a proportion. Now, in terms of what test this is the linear regression t-test. It's referred to often as the beta test, but that's not what it is on your calculator. It's called the linear regression t-test. The null will always be that the slope, the actual relationship beta, is 0, meaning there is no relationship. I don't see any linear relationship at all. And your alternative will be either, it's greater than 0 if it's a positive slope, or less than 0 if it's a negative slope, or it's not equal to 0 if you're just trying to show there is a relationship. Now, the conditions we often remember with this acronym, LINER. Let me explain real quick. L stands for, is the original data linear? Meaning, have you kind of put eyes on a scatter plot? You're not just trusting correlation. You're actually looking at the data. I stands for independent. Okay, and I want to come back to that in a few minutes. But basically, were the data points gathered independently? Are the residuals approximately normal? Meaning most points are very near the line, and as you move further and further from the line, less and less points appear. Most points are clustered near the line. Are the are the residuals equal throughout? Meaning, if we started off with something like this, like here's our line and all the points are really close, but then all of a sudden it starts doing this, and they get further and further as the line goes on, that's not a good fit. We wouldn't want to use a line if that was the relationship. So the deviations should be approximately equal. And finally, did we use a random sample? So linear, independent, normal, equal deviations, and random. Okay. Oftentimes with this on the AP exam, they will just straight say all conditions were met, and you don't have to worry about it. You don't have to repeat it or say anything. Now, this also is a t-test, so that will be what you report back, but this time it is n minus 2 degrees of freedom. And the reason it's n minus 2 degrees of freedom is simply that it takes 2 points to make a line. So we don't have any kind of freedom from our line until we have a third point. Okay, so now we're down to kind of the last ones that are featured on the AP exam. If we haven't hit your test yet, okay, so no, we are down to kind of categories. Things are put in categories with counts, like how many are in each of these groups. And this is the chi-square test. Once again, right here, we're going to count samples. But if we have one sample with one variable, that's a chi-square goodness of fit test. Okay, meaning you just asked everyone, how'd you get to work today? Tell me, did you ride your bike, walk, take public transportation, or drive? Every person gives you one piece of data. Okay? If you had one sample, but more categories, so I'm going to put more than one category, probably two, then it's a chi-square test for independence. And this would be something like, tell me your age, I'll put you in an age group, 20 to 30, 31 to whatever, and how you got to work. So I collected an age to put you in a category, and I collected your method of transportation. If there were two samples, like two separate samples, then it's the chi-square test for what's called homogeneity. Okay. Now, the goodness of fit test, and all of these tests have essentially the same conditions. Obviously, with two samples, we're going to add in that independent samples condition. But they all have slightly different nulls. For this, it's the expected distribution of blank equals the observed distribution of blank. So for my example, I would have said the expected distribution of commuting types is equal to the observed distribution. So what I saw when I took my sample is equal to the expected amount. If I roll a dice, you'd say, well, the expected distribution of 1/6, the same amount of 1 through 6 on the die, is also what I observed. For independence, the null is that those two variables you collected are independent of one another. So you could say how you got to work is independent of your age. And for homogeneity, it's that the distribution for all samples are equal, are the same. I should have said you could have more than one or two samples if you wanted. Let's say, or more. Okay, but you'd assume like, well, I collected data on men and women, and I expect the distribution to be the same for the genders, something like that. Now, for the conditions, we still have this one, but in this case, our other condition is all of our expected counts are greater than or equal to 5. So when you set these up, you're like the expected distribution. You didn't have such a small amount of things in the sample that your expected counts were less than 5. And that would be true on all of these. Your statistic that you report back will be called the chi-square statistic, and it will have degrees of freedom. For the goodness of fit test, Degrees of freedom are the number of categories minus 1 degrees of freedom. So if you broke things into 5 commuting types, you'd have 4 degrees of freedom. For the other two, it is the number of kind of rows in your table, minus 1, times the number of columns in your table, minus 1. So essentially it's, how many samples did you take, minus 1, times how many categories did you break them into, minus 1. Or in the case of independence, how many categories of age, minus 1, how many categories of commute type, minus 1. So when you have the data presented to you in a table, it's going to be number of rows, minus 1, times number of columns, minus 1. So these are all of the different hypothesis tests that will be tested on the AP exam. And this is kind of the progression that I would follow as I'm deciding which one is which. Again, if you want to see actual specific examples, go check my channel for examples of each of these types of tests. But this is the procedure I would use to decide which one to use. If this video helped, please like and subscribe for more math help.